Hi everyone, welcome back to Statistics and Data Analysis. Today we want to talk about sampling, how to get a sample from a population, and more importantly, sampling distributions. We want to understand the sample so that we may infer the population. Okay, let's start. So, when we cannot study the whole population, we choose to study a sample, right? So we need to have different ways to sample from a population. That's called sampling techniques. We need to be able to understand the properties of different sampling techniques so that we know which one to choose. And then we need to have the idea that the sample is unpredictable. Typically, when you sample, you do random sampling, okay? And you cannot predict what's going to be included in your sample. So your sample has a probability distribution that is really required for us to connect the sample with the population. We need to know how your sample how your sample is, what your sample is, so that we may infer the population. Okay, so we need to know sampling distribution. Today we will do this. So let's motivate this study with the candy example. So as you know, my mom asked me to produce bags of candies. The weight should be within 1.8 and 2.2 kilograms. Suppose my mom hope that the defective rate, the probability for each bag of candy to weigh more than 2.2 or less than 1.8 kilograms. My mom hoped that the defective rate would be lower than 5%. But of course, my mom is not me, and my mom does not know what's really the defective rate. So, one thing that my mom can do is, of course, that whatever number of bags I produce, my mom check whether it's good or not to see whether the defective rate is really under control. Okay, my mom will calculate the sample mean. My mom can really calculate the population mean if he wants to do that, if she wants to do that. But anyway, suppose it's not possible, then my mom can choose to do this. Someday she comes to my working place and simply draw one bag of candy. Suppose my mom sees that the weight is 2.1 kilogram. Then my mom may simply say, okay, according to my expectation, is within the standard, so you're safe. Okay, my mom may conclude that the defective rate is less than 5%. Obviously, this is not a very good idea because there's no strong evidence to show you that the outcome of one bag can be related to the defective rate. How about this? If my mom draws 5 bags and see 2.1 kilogram, does that relate to defective rate? Slightly more, but still not directly, right? If my mom can draw if my mom can draw more bags and still see 2.1, my mom should somewhat be more comfortable about the production process, somewhat more confident. That's intuitive. But we don't know how large should be the sample size. And also we don't know what's going to happen if my mom sees the average to be 2.18 kilograms, which is very close to the upper bound. We may always do random investigation to get some random sample, but we want to know how to use the random sample to infer the population. For example, to infer the population mean, the population standard deviation, to infer the defective rate. Okay, that's something we want to do. So we need sampling distributions. Recall that we have 3 pairs of concepts introduced in the first lecture. If we want to study a population, we study a sample. This helps us to get some statistics that can be used to estimate or test the parameters. That's going to require us to do sampling instead of census. Okay, so we need to know sampling distributions so that we can really do the inference. So in the first two videos, I will talk about simple sampling techniques, and then I will talk about what's going to happen to our sample means when we draw a random sample from a normal or non-normal population. Okay, so for sampling is in general just a process of selecting a subset of entities from the whole population. So it's really nothing special. It's just a way to select a subset. Sampling may be either random or non-random. Okay, so if it is a random sampling, that means whether an entity will be selected is probabilistic. Before we do that, we don't know whether one particular item will be selected or not. But if we do non-random sampling, then the outcome would be somewhat deterministic. Okay? For example, if I want to sample from NTU, I may only sample from this class. Then it's deterministic because I know who will be included in my sample. If I do this today, tomorrow, the day after tomorrow, I will always get the same outcome. Then it's called non-random sampling. Most of the statistical methods will only apply to random sampling. Okay, that's because only with random sampling we can make sure that we somewhat get a representative data set. We somewhat get a representative sample, right? If I want to infer the whole population of NTU, all the students in NTU, but I sample only from this class, then obviously there is a deviation. So that's not very good. What I should do is to do random sampling, right? Today we will talk about three popular random sampling techniques: simple random sampling, stratified random sampling, and cluster random sampling. In a simple random sampling, the thing is that each entity, each item, will be set the same probability of being selected. Okay? And that can simply be done with a random number generator that generates random samples with equal probability. For example, the sample function in R that we introduced in the previous week. So as an example, suppose I want to study all those students who graduated from NTUIM, and I want to study the number of units they took before their graduation. Okay, so I certainly may do a census if I have all the data, but let's assume we don't have it, probably because the computer system was broken or all the data was not stored appropriately. So let's assume I have a list of all the graduated students, but I don't know their credits. Okay, then let's assume capital N, the number of people who graduated from my department is simply 1,000. For each student, if I randomly select him or her, then I would ask whether she has double majored when she was in the university, and when did she graduate, and the number of units that she took when she was an undergrad student. Okay, so I know if I can really ask everyone, I would be able to prepare a table like this. Okay, I somehow number all the students, or maybe for example by the alphabetic order. Then for the first guy, I know whether he double majored or not, the year of class, and the unit, and so on and so on. I'm going to have 1,000 1,000 students record about it. But now I just don't have this table. Okay, I'm going to randomly select 200 students and ask them about this. So later I'm going to have 20 records about this. So how may I do that? Among 1, 2, 3, 4, blah 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 to 1,000. Among these 1,000 numbers, I want to randomly generate 200 random numbers. Okay, as you know, we may simply do this by calling the sample function in R. The first parameter is the population, and the second parameter is the number of samples we want. Okay, you know there is a difference between sampling with replacement and sampling without replacement. Okay, think about which one to use and how to do that in this example. Now you know it. But anyway, suppose we got these 200 numbers. Then all we need to do is say, okay, well, I got number 2, so the second student should get a call from me, and I will ask whether he double majored, when did he graduate, and how many units did he took. I also get number 7, so I will do the same thing on number 7, and so on and so on. So I will get 200 records. Okay, and then I have a random sample. That random sample can be used to calculate the sample mean, sample variance, whatever probability, or how many boys are there, how many girls are there, and so on and so on. Okay, that's a random sample that I can play with. So obviously, the upside of simple random sampling is that it's very simple. We don't really need to worry about how to assign probabilities for each entity to be selected. We simply assign equal probability to everyone. Okay, that's something we will do. The bad thing is that we may generate non-representative samples. What does that mean? Sometimes in simple random sampling, we may get too much data that fall in the same stratum or the same category. If that's the case, then our sample may not be representative to the population. For example, when we select 200 students, it's possible that we are unlucky and all those 200 students did not double major when they were undergraduate students. If that's the case, then our, for example, sample mean will somewhat be underestimating the population mean, the mean of all the 1,000 students, right? So we may need to take this into consideration when we do sampling. As another example, suppose now I try to sample 1,000 voters in Taiwan regarding their preference on 2 candidates. If that's something I want to do, and I do simple random sampling, some bad things may happen. For example, probably around 1/2 voters are men, but in my random sample I am unlucky and get 65% voters that are men. Okay? Then if men and women tend to have different preferences, then my result would be somewhat misleading. Similarly, if around 28% voters live in Taipei, but in my sample I got around 40% voters in Taipei, then my result may be somewhat misleading if their preferences are different according to where they live. Okay, so if we know there is some factors that may affect the outcome, that may affect the property of that of those data in that stratum or in that category, then we need to be more careful when we do random sampling. So that's why sometimes we will adjust the simple random sampling process to stratified random sampling. We will talk about that in the next video. Thank you.